going to finish up section 7.2. And first thing we're going to look at is how we can take a function that has trig and get rid of the trig and turn it into something equivalent with just algebra. All right. So here's an example of a formula that has trig. How do we know that that formula has trig in it? What kind of gives it away? Yeah?
Sine, inverse, cosine.
Yeah, sine and inverse cosine. Those are trigonometric functions. Okay, what I want to do when I'm done is put something in that box that gives me the exact same result as that formula on the left, but it has no trig in it. That means you can't use sines, cosines, tangents. You can use anything else. You can use adding, subtracting, multiplying, dividing, squaring, square rooting, any of that stuff. Okay, that's not trig. Okay. So that's what I want to figure out how we can do. So when we do that, we're going to have two different functions that we're working with. Okay. I'm going to call this one the inner, and I'll call that one the outer function. When we start with the inner function, what we're going to do is try to set up a picture. So we're going to convert the inner function more into a picture. And that's exactly what I tried to do in the homework when it said to solve that problem without a calculator. And it said like inverse sine, and then we drew it out. That's what we're going to do. Okay. In order to draw that right triangle diagram, remember they gave us something in the book in terms of inverse trig. And I said there's two ways you can think about it. You can think about it as inverse trig, or I think we took the cosine of each side or the sine of each side. But whatever we did, we got rid of the inverse trig and we rewrote it using regular trig. That's what we're going to do here. Rewriting an inverse trig expression in terms of a regular trig expression is going to help us to draw that diagram. Now, if the inner function is not inverse trig, well, we'll do one of those. But most of the ones we focus on, it is going to be inverse trig on the inside and regular trig on the outside. Okay. Once we draw that right triangle diagram, you're only going to have two of the sides labeled based on the information that you're given. But if you know two sides in a right triangle, how can you get the third one? Yeah?
A squared plus b squared equals c squared, or Pythagorean theorem.
Yeah, we can use Pythagorean theorem to get that third angle. Sorry, to get the third side. All right, so we'll go through the process a couple times. We're going to try it first in more of a generic way with just letters, and then we'll actually do a specific one with numbers. Okay, but I do want to try it first with letters because that's mostly what you're going to see on the test. All right, so let's try this one. It says to write an algebraic expression in terms of v. V is just the variable they're using. It could be v, x, y, q. That doesn't matter. It's just the letter. All right. So what function did I say to start with? The inner or the outer? Yep. Inner. So we're going to forget about sine. We're not even going to deal with sine until the very last step in this problem. Okay. Everything we do right now is going to be focused on inverse cosine. So let's write that down. Now, I don't know what's in that red box. I don't know what that's going to come out to. I don't know the number. But I do know that when I use inverse trig, I'm always solving for the
Angle.
I'm always solving for the angle. I don't know what angle I'm solving for because that's a variable. But I want to represent it generically. How do we represent an angle generically in trig? Yeah? Yeah, theta, alpha, some Greek letter. Okay, so for now, let's just say what's inside that red box is going to come out to some angle. I don't know what angle, but some angle. All right. Now the next step, I don't want to think of this as inverse trig. How do I want to think of this line, this equation right here, in terms of what? So think about what we did in the homework and that problem where it said solve without a calculator. We had something like that. We had an actual number for v, but this time we don't have a number. Yeah. Right. I want to think of that in terms of regular trig because when I'm drawing a right triangle diagram, that's the easiest way to think about it. So we're going to take the cosine of each side. Okay. This doesn't solve anything. It just manipulates the expression in a way that it's going to be easier to draw a right triangle diagram for. When I do that, Dex, what do I have on the left?
Is it just cosine? Oh, just v?
No, on the left, the cosine and inverse cosine are gone.
Just v?
Yep. And then how about on the right?
Cosine theta.
Cosine theta. Okay. So now I'm getting ready to draw a diagram for that. In order to draw a diagram for that, I always want to think of that as a fraction. How can I make v a fraction without altering its value? Yeah?
V over 1.
Yeah, let's do v over 1. So now we need to draw a diagram with theta in it, and I need to label it so that the cosine is v over 1. Okay. Doesn't matter where you put the acute angle, it just has to be either one of the two. And now they've given me the cosine. If you know the cosine of an angle, what two sides have they really told you some information about? Yep. The adjacent and the hypotenuse. So we know the adjacent is how long? V, and the hypotenuse? 1. Okay. So what we've just done there is we've converted this red box into an image. That picture represents exactly what's happening in that red box. Now, we want to take the sine of what's inside the red box. So we want to take the sine of the picture that we just drew. Okay. What's the formula for sine? Yep. It's opposite over hypotenuse. But what's wrong with trying to take the sine the way we have that right now? What's going to happen if we try to take the sine of theta? Yeah? We're missing the opposite. So now we have to figure out the opposite to be able to take the sine, and then we'll be able to write the answer. Okay. How am I going to find the opposite? What can I do? Yes? Yeah, we can do Pythagorean theorem. We can give it a name temporarily. If you want to call it A, just temporarily, that's fine. But we're going to have an expression for A in a minute. Can anybody set up my Pythagorean theorem for me with those 3 labels? Yeah?
A squared plus b squared equals 1 squared.
Okay, so a squared plus v squared equals 1 squared. And if we solve that for A, can someone tell me what would go inside that box? Yeah.
1 squared minus b squared. Or, I don't know.
So 1 squared minus v squared would be something, but it's not A. Yeah?
The square root of 1 squared minus v squared.
Right. We got to take the square root of that. what you had said was a squared. Okay, so we want a, which is the square root of 1 minus v squared. Okay, so now we can label this side 1 minus v squared. We have all three sides labeled, so now we can find any trig function they want, and specifically, they want to know the sign. So we said sine is opposite over hypotenuse. So in this case, opposite is 1 square root of 1 minus v squared. Okay, divided by the hypotenuse. We don't need it this time because the hypotenuse is just 1. So that formula on the right is exactly the same as that formula on the left. They each do the same thing. The difference is the left formula gets the result using trig. The right formula gets the result using purely algebra. Or, yeah, arithmetic that's not trig. All right, let's try it. Let's pick a number for v and plug it in. Okay, remember, the domain here is -1 to 1. You're restricted by that because that's the domain of inverse cosine. But that's good because if you didn't use numbers between -1 and 1, what would happen on the right side? If you plug in like 5 for v, which you're not allowed to do based on this function on the left anyway. Yeah? So what would happen?
The side would be negative, and it just came out a negative sign.
So something with a negative, but I'm thinking more something else would happen because of that negative. What would happen if you try to plug in like a 5 on the right side? What kind of answer would you get? Yeah?
Like not a real number.
Not a real number.
Because you can't square root.
Yeah. So what kind of number would you get? Yeah. Imaginary. Okay. So you can't plug a number in that's not between -1 and 1 anyway because of the restriction on the domain from the left side. So that automatically takes care of the fact you will never have a negative square root on the right. That can't happen. All right. So let's try picking a number between -1 and 1. Let's do 0.34 and plug it in. Okay, so we want to make sure we are in radians. And let's do the sine of the inverse cosine of 0.34. That's the result using the left-hand formula. Now let's try it on the right and plug in 0.34 for v. So square root of 1 minus 0.34 squared. I get exactly the same answer. That doesn't prove the formula is right. The work we did proves that it's right. But that's an example of how you plug in a specific number and you get the same result on the left and on the right. Okay? Another way you could also verify, instead of plugging in a specific number, plug in every number, okay? Graph it, and see what that looks like. Again, a graph is still not a proof. Just because two graphs are going to look the same doesn't actually mean anything. They could be off by just like 0.000001, and you can't see that when you're graphing it. But if two graphs look identical, then it suggests that the two formulas are probably the same, and we know they're the same because we proved it doing out the algebra. Okay. So let's type in square root of 1 minus x squared. Let's do zoom 7. I think that window, I might have to zoom in a little better for you to see it. But the left formula is using algebra. Okay, so watch it do its thing. And the right formula uses, the left formula was trig, and the right formula was algebra. What did you notice as it graphed it, the difference between the left one and the right one? Not the end result. The end result looks the same. But how about as it was graphing? Yeah?
The blue one was
The right one was faster. So that starts to become important if you're building an algorithm or something into a computer and you want to get the same result, but you want to get it faster. All right? The right formula is a more efficient way, at least with how this calculator does its math, it can do the right way faster than the left way. Maybe it's because the trig is more complicated and the calculator has to go through more steps to get the same result. Okay. All right. Any question on that one? All right, let's try this one. This is the tangent of the inverse sine. Bless you. Okay, so when I'm done, I want a formula. No square roots in the bottom. If that happens, we'll take care of that as well. Okay, so I've shown you how to do it one time. Can somebody walk me through, not every step, just tell me my first step. Yep.
Do the inner first.
Take the inner, okay. Okay, set it equal to theta. That's a good first step. Now, can somebody give me my second step with that equation? Yeah.
Multiply both sides by sine.
I'm being picky, but there's a reason. Yeah.
Take the tangent of both sides.
No, we were closer before. So combine the two things you said somehow. Yep.
Take the sine of both sides.
Take the sine of both sides. Okay. So when you do this, it's important to understand you can't multiply by a word. You can multiply by a variable or a number. That's a function. So we're taking the sine of what's on the left, and we're taking the sine of what's on the right. Those cancel. Now, I have v equals sine theta. All right. What do I want to do at this step? Yeah.
You want to divide v by 1.
Yeah, it's a good idea to start thinking of that as a fraction. If it was already a fraction, fine. But if not, you probably want to make it one because of the next step. And what's my next step now? Yeah,
Draw a picture.
we're going to draw a picture. Can you be more specific with what kind of picture? Just like,
Right triangle.
here's our picture. Oh, okay, we want to draw a right triangle picture. Good. Okay, so we got a right triangle. We're going to put theta in it somewhere. And now, once we put in theta, we need to start labeling the sides. How do we use that information we have to label those sides? Yeah.
Isn't one side v, which is the opposite side of theta?
The opposite side is v, yes. Yep.
And the hypotenuse is 1.
Hypotenuse is 1, okay? And now, using the picture that we just drew for this, we want to take the what in our picture. Or we want to find the,
A or v, what picture?
what is it that they gave us and they said to find? Yep.
V.
The tangent.
We want the tangent. What's the definition of tangent? Yep.
Opposite over adjacent.
Opposite over adjacent. The problem is we don't know adjacent. So how are we going to find the adjacent? Yep. We're going to do Pythagorean theorem, but that's the same triangle we just did last time. You have v for a leg, 1 for the hypotenuse. You can really just copy the answer from up here. It's going to be the square root of 1 minus v squared. Again, it's the same triangle. Now, using the definition we just said of tangent, tangent is opposite over adjacent. So the opposite is v, and the adjacent, square root of 1 minus v squared. Okay. What do I get when I fix that so the square root is not in the bottom? Yep.
V times the square root of 1 minus v squared over 1. Or no, over 1 minus v squared.
Yes. So that formula on the right is exactly the same as the formula on the left. The difference is the left uses trig, the right has no trig in it at all. All right. Any question how we converted that formula to not have any trig? And that's pretty much the same process for every function that has a regular trig function on the outside and inverse on the inside. Okay. All right. It's kind of the same thing. There's nothing new in that problem. So let's try this one. That's different. What's different about this one? Yeah?
We have an actual number this time.
Okay, so we don't have any variables, which means we evaluate. We're actually going to get a numerical answer. There is something else different. Yeah?
The inverse is on the outside.
Yeah, we've got the inverse on the outside. Okay, so we might still end up drawing a right triangle. We'll see. But we need to kind of think of this like PEMDAS, follow order of operations. Start with what's inside the parentheses, and let's see if we can figure out that. Right? So we're going to forget about inverse sine for now and see if we can figure out the tangent of 3 pi over 4. Okay. What is that in degrees? This might make it a little easier to think about. Yeah.
135.
That's 135. Good. Okay. 135 is a multiple of what number? Yeah.
Isn't it a multiple of?
It's a multiple of a few different numbers.
45?
But yeah, I'm thinking it's a multiple of 45, which is why we can figure this out without a calculator. So now this is going to tie in with the kind of like the question you had in the homework. So we're going to find the tangent of 135. We know it's in quadrant 2 because angles between 90 and 180 are in quadrant 2. Is it closer to 90, 180, or right in the middle?
Right in the middle.
It's right in the middle. So put a point that marks 135. Make a triangle out of it. And we're going to think of this using unit circle trig. That's a 45, 45, 90 triangle. In the unit circle, how long is each leg in the 45, 45? Yeah.
Square root of 2 over 2.
They're both square root of 2 over 2. So now when we write the coordinate for 135, we have to take into account we went left and we went up. Okay. So what is the coordinate for 135? Yeah,
Negative root over 2, and then over 2 over 2.
good. Okay, so now we've got the coordinate. Now we can figure out the tangent. What's the formula for tangent on the unit circle? That's your x, that's your y. Yeah?
Opposite over adjacent.
Well, that's in a right triangle. But how do we think of it in a unit circle? It's similar. Yeah?
X over Y.
Nope, that's the cotangent.
Um,
Y over x. Okay, so the tangent is y over x. If you take y and you divide by x, what do you get when you do y divided by x here? Yep, you get -1. So now we know the tangent of 135, without using a calculator, is -1. Now that simplifies the original problem. They want the inverse sine of -1. Okay. If you're kind of stuck thinking of it as inverse sine, then think of it as regular sine, whichever way makes more sense to you. When I take the inverse sine and I get an answer, what kind of answer am I going to get?
Angle.
I'm going to get an angle. I don't know what that angle is right now, but that's what I'm solving for. If you take the sine of each side, you would have this. The sine of theta has to equal -1. So the question is, what angle can you take the sine of? And the answer comes out to -1. Well, easiest way to think of that is probably a picture of sine. Here's your sine function. 0. Let's mark all these points. Pi over 2, pi. 3 pi over 2, 2 pi. So what angle in that picture could you take the sine of? And the answer comes out to -1.
3 pi over 2.
3 pi over 2. Yeah. If it didn't come out to a -1, if it came out to like a -0.65 or something, well, we wouldn't be able to figure that out. Only reason we can figure that out is because -1 is the very bottom of the wave. We could do a -1, we could do a +1, and we could also do a 0. Any of those three numbers we can figure out. Anything that's not those, you'd need a calculator. Okay. So the answer is 3 pi over 2. That's final answer to the question. Okay, so that's a really good question because it ties in all kinds of things from trig that you really need to understand. Basic things like converting a radian to a degree just to visualize it, unit circle trig, graphing a sine function. Any question on that? Okay, and if you're wondering, well, why can't you just type it in? Well, first of all, if you try to type this in, it's not going to give you 3 pi over 2. It's going to give you a decimal. Negative inverse sine of the tangent of 3 pi over 4. It gave us negative 1.57. We got, okay, so I'm going to show you what we got. We got that. What's the cycle of, let's think of the cycle of the like sine or cosine function. How long does it go before it repeats? Yep.
2 pi.
2 pi. Take the answer that they got, or take our answer, and subtract 1 cycle. It is the same thing. All right? It is the same. So it's just a difference of which cycle you're writing the answer in. I would accept either answer for that question. All right. Any question on that? What I would probably do is specify, write your answer as a positive number or write your answer as a negative number, and then you would know, okay, if I don't get a positive number, I can add a multiple of the cycle to my answer to make it a positive number. All right, let's try one more of those, and then we'll finish up with solving an equation. Okay. This one is similar to the first ones we did, but there are no variables. So when we're done, we're going to get a numerical answer. Okay. And again, if you're wondering, well, why can't I just do the cosine of the inverse sine of 0.5? Because I want that as an exact number. Now, you might say, well, I still recognize that as square root 3 over 2, if you know your decimals in unit circle trig. Well, that's great because this one came out to a common decimal that should be recognizable, but that most of the time won't happen. You're probably going to get a decimal here that you don't recognize at all if you try to type it in. Okay? And the directions will ask for an exact answer. So let's figure this out just like we did the first couple problems. Okay? Then you don't have to worry about a decimal or even using a calculator at all. Okay. What trig function do we start with?
Inverse sine.
Inverse sine. And what are we going to set it equal to?
Theta.
Set it equal to theta. And now what am I going to do on both sides?
Take the sine of both sides.
Yep, I'm going to take the sine of both sides. And now I have 1/2 equals sine theta. My next step would normally be to make this number a fraction. It already is. So we're good with that. Now we draw a diagram. Nick, what two sides can I label based on that information? And tell me what numbers I should use.
You can do the opposite be 1,
Mhm.
and adjacent be 2. Oh no, hypotenuse is 2.
Hypotenuse is 2. And then use your Pythagorean theorem. Or recognize that as a special right triangle. Again, I would just use Pythagorean theorem because you might not have a special right triangle all the time. But that's what you get if you use Pythagorean theorem. Okay. Now we want the cosine. Cosine is adjacent over hypotenuse. Adjacent is square root of 3. Hypotenuse is 2. And I knew that it was root 3 over 2 by looking at that 0.866 number. But I might not always be lucky enough to recognize the decimal I see as a special fraction with a square root. Okay? And if you do it this way, you don't have to. All right? In fact, I'm going to give you one on the test that the number you get here is not a number you've seen before. It might be like square root of 7 over 13. Right? It's not going to be something you could recognize easily. But you don't need to, as long as you do it this way. All right, any question on that? All right, so last thing we're going to look at is solving some trig equations using the calculator and a chart we started to look at. We're going to finish that chart today. Remember that when you are finding answers to a trig equation, there are an infinite amount of answers. Well, there's either an infinite amount of answers with the kind of equations we're doing, or there's no answer. If you were trying to figure out where that wave hits 0.7, you would draw the wave, you'd put a line at 0.7, and then you could find the intersections. Now, if I say to only find the answer in the first cycle, you look at something like that, and then you get your two answers. If I say to find all solutions, then finding 2 is not all. Okay? You have to find the 2, but then you have to put something on the end of it. Does anybody remember what you put on the end of an answer that indicates that it keeps repeating? Well, how often, let's say we'll call this one the blue answer. The blue answer occurs again right there. How far apart are those two blue dots in general? Don't.
1 cycle.
1 cycle. So does anybody remember, once you know this answer, what do you put on the end of it? You put plus something to indicate that it's going to repeat every cycle forever. Let's say this is the sine function, regular, normal period. Yep.
2 pi x.
Yeah, you put a plus 2 pi, and you usually pick a letter, like plus 2 pi n, 2 pi k. What that indicates is you can add any multiple of 2 pi to your answer to get the next one. Or if you add it again, you'll get the next one after that. So the way we can figure out these first two, and the way we did it before, is we graphed it. We did a y1 for the wave. We put the horizontal line in y2, and then we did second calc intercept. Well, now we don't want to do it that way. We want to use inverse trig to get the variable by itself. The problem is, we talked about inverse trig yesterday. Inverse trig, inverse sine, inverse cosine, and inverse tangent are all functions. When you have a function and you type a number in, by definition, how many answers do you get? if something is a function? Yep, we get 1. There's 2 there. So how do we get that second answer then if we're going to use the inverse sine function to solve it? That's where a chart that we did is going to come up. We had this chart, and we talked about it with reference angles. I'll draw the first one, but then I want to erase it because if I draw them all, it starts to look pretty messy. Let's say that you had a triangle in that quadrant, and you had an angle right there. That angle is called your reference angle. But what I want to know is how I could use that reference angle to get this entire angle. Does anybody remember, if you know this, what do you do with it to figure out that angle? Yep.
You subtract it by 180.
Yeah, you subtract it from 180. So in quadrant 2, the formula that we need to remember is 180 minus the reference angle. In quadrant 1, there is nothing special. The answer you get is the reference angle. Okay, reference angle is a positive angle between 0 and 90. So if it's already in quadrant 1, you don't have to worry about anything. Now, what if you had a triangle like this? That's your reference angle from here to here. But I want to know that angle from there to there. What's the formula in quadrant 3 if we want to get this entire angle and we know the reference angle? Yep.
180 plus ref.
Yep, 180 plus the reference angle. And the formula in quadrant 4,
360.
I'm not going to go through the whole thing, but it is 360 minus the reference angle. So that gives you a formula you can use to find answers in other quadrants. But how do you know which quadrant the other answer is in? Right? That's where this part comes in. ASTC. A means all trig functions are positive. All trig functions are positive. So if you pick an angle between 0 and 90 degrees, and you take the sine, the cosine, or the tangent, every single one of them will come out positive. 54.7. The sine of 54.7, well, if you do it in degrees. If you're in radians, then you need to be between 0 and pi over 2. That's between 0 and 1.57. My calculator was in radians, and I did not type in a number between 0 and 1.57. I meant to be in degrees. So let me do this in degrees. Okay. Now I'm in degrees. Pick a number between 0 and 90. Sine of 54.7 comes out positive. Cosine 54.7 comes out positive. Tangent of 54.7. They all come out positive in quadrant 1. You will never get a negative answer in quadrant 1 when you do sine, cosine, tangent, or their reciprocals. Because flipping something that's positive, it's still positive. Let's look at quadrant 2. Quadrant 2 are the angles between 90 and 180. In quadrant 2, only sine is positive. So pick an angle between 90 and 180, 133. If you type that in on the calculator, because that's in quadrant 2, the sine will come out positive. Everything else will come out negative. Sine is the only positive trig function out of those 3 in quadrant 2. So now if the sine is positive, what other trig function technically is also positive?
Inverse sine.
No, not inverse sine. sine and the cosecant, right? Because it's a reciprocal. So when I just mentioned the sine, the tangent, and the cosine, their reciprocal is also positive. It's just simpler if I only draw that in the diagram. What trig functions do you think come out positive in quadrant 3?
All tangent function.
Just the tangent. Okay, so the t, that's quadrant 3. T means only tangent is positive. And which trig functions do you think come out positive in quadrant 4?
Cosine.
The cosines. Okay, so without thinking about the reciprocals, there are 2 quadrants where these 3 trig functions are positive, and there are 2 quadrants where those 3 trig functions are negative. There's 2 of each. And now, knowing whether something is positive or negative, and then knowing a formula in each quadrant will help us to find both those answers without any graphing. Okay. All right, so let's try it. First, let's look at that and let's identify what quadrants our answers are going to be in. Okay. You have sine equal to a positive number. 0.6 is a positive number. What 2 quadrants does the sine equal a positive number? Yeah, 1 and 2. So off to the side, I'm just going to write that down to remind me I'm looking for answers in quadrants 1 and quadrants 2. Let's start with the first answer. Okay, I need to get rid of the sine in that function and get x by itself. How am I going to get rid of sine? Yep.
Take the inverse sine of both sides.
And take the inverse sine of both sides. Okay. And let's see what answer that gives us, and it better be in line with either quadrant 1 or quadrant 2. Okay. So inverse sine of 0.6. Did I get a quadrant 1 or a quadrant 2 answer?
Quadrant 1.
That's a quadrant 1 answer. Yep. 36.87 degrees. And that is my what angle?
Reference angle.
That's my reference angle, 36.87. Now, we're going to plug that in to the formula we need to. Okay, we're supposed to find another answer in quadrant 2. In quadrant 2, it's 180 minus the reference angle, 143.13. That, well, actually I should go like this, because I need to add something onto it. Those are my first 2 answers. Okay. We can check it if you type it back in. Take the sine of 143.13 and you get 0.6. Take the sine of 36.87 and you basically get 0.6. So we know that those 2 answers are right. Now, I want to represent those 2 answers repeating. So what do I need to add on to the end of each one of those answers? Yeah?
Plus 2 pi and then whatever variable we want, like h.
Okay, so we usually use n or k. Technically, you could use anything. But that's not quite what we would want to add onto the end.
This is in degrees.
This is in degrees.
So it'd be plus 360 degree, or 360 in k degrees.
Yeah. That means you can add any multiple of 360 to those answers. And you'll get another answer in a later or earlier cycle. It would be an earlier cycle if k was a negative number. So remember, k has to be an integer. That's important. K is an integer. All right. Now, this last one kind of gets at this point right here. We don't have buttons for working with inverse cotangent on the calculator. So we can't think of this as cotangent. But what function is related to cotangent? Yep. Tangent. Yeah. So if they tell you the cotangent is 2.5, what's the tangent? We automatically know that too. Yeah.
1 over 2.5.
It's the reciprocal. Now we've got a problem we can figure out. Okay. What quadrant am I looking for an answer in? Where is tangent positive?
1 and 3.
1 and 3. When I do the inverse tangent of 1 divided by 2.5, I do get an answer in quadrant 1, 21.80. The formula in quadrant 3 is 180 plus your reference angle. So you might think, well, the other answer is 201.80. But what's the cycle length of tangent? It's not 360. Yeah?
Isn't it 180?
It's 180. So tangent, it's not a great drawing, but it looks something like that. When you draw in this line, the first answer is right here. The second answer you found is right there. That answer is a repeat. If you add any multiple of 180 to that answer, you will automatically get the second answer. That didn't work up here. If you add multiples of 360 to 36, you will never get 143. Those are two different answers. But these are exactly the same answer. So you don't need to write that second one because it's included in the first one. Okay. So that's something we have to check when we write our final answer and make sure we're not really writing the same answer twice. Right. But that's how you do the cotangent of 2.5. Cotangent equals 2.5. Right. And we can practice some more of those tomorrow. So there aren't that many questions left to look at. There's 10 or 11 questions, 12 questions, I don't know. So we'll look at that tomorrow, and then that finishes up section 7.5.